Very good morning, students.
Good morning, sir.
Good morning, sir.
Good morning.
Good morning, sir.
Good morning, all of you. So, last class, if you remember what we have discussed, we have discussed about alcohols. Yes or no? The preparations, properties, reactions involving cleavage of CO bond, reactions involving cleavage of OH bond, and the last set of reactions which we have discussed in alcohols are what are the last set of reactions, students? The Victor-Mayer test. Yes, Victor-Mayer test, which is used to distinguish between primary, secondary, and tertiary alcohols. Primary alcohol will give red colored salt, secondary alcohol will remain blue, and tertiary alcohol no reaction. That means it remains colorless. Okay. And before this Victor-Mayer test, we have seen about different reactions, like oxidation reactions we have seen. Yes or no? Strong oxidizing agent, milder oxidizing agents. What is going to happen? Now we'll start with one more oxidizing agent and then go with the electrophilic substitution reactions of phenols. Yes or no? Last class we were supposed to start with the electrophilic substitution reactions of phenol. But before that, we'll discuss one more oxidation of alcohols, that is oxidation using HiO4. Let us take a dihydric alcohol CH2H. Oxidation using HiO4. Let us take dihydric alcohol CH2OH, CH2OH, and treat this with HiO4. HiO4 means what? We will get H plus and IO4 minus ion. IO4 minus will be having a respective resonating structure in this manner: I double bond O, I double bond O, I double bond O, IO minus. Yes or no? This will be with respect to IO4 minus N. So whenever you treat CH2OH, CH2OH with HiO4, can I say lone pair of electrons present on oxygen, they are going to attack the H plus? That is going to be the first step, obviously, because the lone pair of electrons present on oxygen, they will be acting as a nucleophilic, and they will be attacking the H plus ion. As soon as they attack, you will be getting a protonated alcohol. You will get CH2OH2 plus, one lone pair of electrons on oxygen as it is, and a positive charge, and you will have CH2OH, and you will have CH2OH, right? After that, what is going to happen is, whatever the IO4 minus ion we have, the negatively charged oxygen from the IO4 minus, that can try to attack this electrophilic carbon or not. Look at this reaction. We have IO4 minus in the reaction mixture. I double bond O, I double bond O, I double bond O, O minus. This IO4 minus ion with a negative charge on oxygen, that will attack this particular electrophilic carbon. Why I am called this as an electrophilic carbon? Because the CO electron density has a tendency to move towards oxygen. So as soon as it attacks, you will be getting what, students? CH2 will form a new bond with oxygen, CH2O. Negative charge on oxygen should be nullified because it has donated the electron density. The partial positive charge on carbon should also be nullified. CH2O, oxygen should be connected with iodine, iodine connected with double bond O, double bond O, double bond O. Yes or no? And you will have again CH2OH as it is, CH2OH as it is. And if you look at iodine and oxygen, which is more electronegative? Oxygen is more electronegative. So the pi electron density has a tendency to move towards oxygen. If the pi electron density is moving towards oxygen, the iodine develops partial positive charge. So the lone pair of electrons on the other oxygen atom, they will attack the iodine. The pi electron density subsequently move away. In that context, you will be generating CH2O, I double bond O, CH2. Oxygen used its lone pair, so only one lone pair will be present, and other is a positive charge, and OH bond is as it is. And oxygen iodine new bond has been formed, and pi electron density moved away from iodine towards oxygen, so that oxygen will be getting negative charge. So we'll be getting negative charge on this oxygen. So the negatively charged oxygen will try to pick up this proton or not. Why? Because we have OH bond, oxygen bearing positive charge, so OH electron density is moving towards oxygen. Because of that movement, hydrogen develops partial positive charge. So negatively charged oxygen will try to pick up this proton. OH electron density is given to oxygen. Generating what, students? Generating CH2O, I double bond O, I double bond O, IOH, O, CH2O. That means you are going to generate a 5-member ring in this fashion. A 5-member ring is going to be obtained in this fashion, like CH2O, I double bond O, I double bond O, IOH, IO, CH2, CH2. So now this 5-member ring with the 2 oxygen atoms is unstable because of repulsions. So immediately the bonds are going to be cleaved. So this carbon-carbon bond is going to be cleaved. This iodine-oxygen bond is again going to be cleaved. And you will be having scenario like this. So this carbon will be hitting CH2O. CH2O means HC double bond OH. Along with that, this carbon will also get a HC double bond OH. And you will get a iodine will be converted to HiO3. The HiO4 is converted to HiO3. That means CH2OH, CH2OH, whenever you have taken, you form Hc double bond OH plus Hc double bond OH plus HiO3. So that is the main logic behind this conversion. You may ask a question, sir, do we need to do all this mechanism again? No. But what you should know, that means which type of alcohol will form what type of acid or carboxylic acid or aldehyde. So we'll be giving the shortcut. Note down the shortcut. Shortcut is whenever we have CH2OH group, CH2OH will be converted to respect to HC double bond OH. Okay, first point. Whenever you have CHO, that is C double bond OH group, CHO, or CHOH, that is secondary alcoholic group, CHOH. In that case, that will be converted to respect to formic acid, HC double bond OH. That means the primary alcoholic group will be converted to formaldehyde. The aldehyde group or the secondary alcohol, primary alcoholic group will be converted to formaldehyde. Aldehyde or secondary alcohol will convert to respect to formic acid. And if you have a ketonic group, that is C double bond O group, that will be converted to respect to carbon dioxide. Understood this point or not? The primary alcoholic group will be converted to formaldehyde. Aldehyde or secondary alcoholic group will be converted to respect to formic acid. And if you have ketonic group, that will be converted to respect to carbon dioxide. Now the question we are going to ask is, if I take glucose, which has been treated with excess of HiO4, you will get some X moles of Hc double bond OH plus Y moles of HC double bond OH plus some Z moles of CO2. What is the value of X plus Y plus Z? So glucose, what is the structure of glucose, students? Anyone know the structure of glucose? You might have studied biomolecules. In the structure of glucose, you will be having CHO, CHOH, CHOH. Like ultimately, you have CHOH taken 4. CHOH taken 4. Finally, CH2OH. In the glucose, we have an aldehyde group, 4 secondary alcoholic groups, and 1 primary alcoholic group. So we'll get what? Excess HiO4 if you treat. The aldehyde group will be converted to what? The aldehyde group will be converted to respect to formic acid. CHOH taken 4, that is CHOH. The Fisher projections we are going to indicate, like at what carbon OH is on which side, left side or right side. We'll discuss that in the biomolecule chapters in detail, Haworth notations and all. But as of now, what you can say, the aldehyde group is there, and we have 4 secondary alcoholic groups. The aldehyde group or secondary alcoholic group will be converted to respect to formic acid. So in total, you will get 5 moles of HC double bond OH. And you have 1 primary alcoholic group. The primary alcoholic group will be converted to formaldehyde. So 5 moles of HC double bond OH plus 1 mole of HC double bond OH plus 0 moles of CO2. So what is the value of X? X is formaldehyde. So 1. So X is equals to 1. Y is equals to 5. Z is equals to 0. Okay. So X plus Y plus Z is equals to 6. Similarly, if I take fructose, in fructose, if I treat fructose with excess HiO4, same reaction. In fructose, what do we have? What is the structure of fructose?
Ketone group is present in second
Yeah,
carbon.
ketone group is present, and the 2 terminals we have CH2OH, CH2OH. That means 2 primary alcoholic groups. So we have CH2OH, C double bond O, CHOH taken 3 times, and then CH2OH. In total 6 carbon should be there. 1, 2 plus 3, 5 plus 6. So 2 primary alcoholic group will lead to the formation of 2 formaldehyde, 2 HC double bond OH. Ketonic group is present. Ketonic group will convert to CO2, 1 mole of CO2. 3 secondary alcoholic group will form formic acid. So 3 HC double bond OH. Okay, so what is the value of x? X is equal to 2 here, y is equal to 3 here, z is equals to 1. So x plus y plus z again is equals to 6. Okay, they don't be asking only value of x plus y plus z. They can be asking xy by z, xz by y, like the different questions can be framed. Understood this question or not? HiO4 treatment, and that was a mechanism which was discussed in the previous slide. We get a 5-member ring, the bond cleavage occurs in this fashion, and the shortcut is the primary alcoholic group will form formaldehyde, the aldehyde group or secondary alcoholic group will form formic acid, the ketonic group will form respective carbon dioxide. Right, students?
Yes.
Yes.
Yes, right. So then we'll be discussing about, as I have told you, the next set of reactions are reactions of phenols. Phenols undergo electrophilic substitution reactions. Electrophilic substitution reactions is a characteristic reactions of benzene and its derivatives. We all know the same pi electron and state attacks the electrophile. So the pi electron and state attacking the electrophile is the rate determining step, and then you generate a Wheeland complex. This is not aromatic, it is just resonance stabilized. To gain the aromatic nature, the nucleophile will try to pick up the proton, and ultimately you get electrophile is going to be substituted. This is the general mechanistic approach. Let us now look at the same scenario for phenol. In phenol, we have OH group connected to benzene. OH group is electron donating group or electron withdrawing group?
Electron donating by mesomeric.
Electron donating group. Yes or no? By
Mesomeric effect.
mesomeric effect. So OH group is a very good electron donating group because of its electron donation, because of its strong electron donation. What you are going to have is the electron density at ortho as well as at para positions is going to be increased greatly. The electron density is going to be increased greatly at ortho as well as at para positions. So because of the increased electron density, whenever I am trying to do the nitration, if I use concentrated HNO3, what is going to happen is the NO2 group, the NO2 electrophile is going to be substituted at all the positions, all the 3 positions. So let us first draw the resonating structures. So at the ortho and para positions, you have negative charge. The negative charge is developed at ortho as well as at para positions. And now if you have to do nitration of phenol, then what is going to happen in the case of concentrated HNO3 is concentrated HNO3 will generate the electrophile greatly. More electrophile concentration. More is the electrophile concentration. All the 3 positions, that is both the ortho and 1 para, they are going to be substituted by electrophile. So you get NO2 placed at 2 ortho and 1 para, that is 2,4,6 trinitrophenol or picric acid is obtained along with some oxidized products, that is quinolines are also going to be obtained. If you want to produce only mononitration product, in the case of only obtaining mononitration, you have to use dilute HNO3. In the presence of dilute HNO3, since the HNO3 concentration is less, so NO2 plus is going to be substituted only at either ortho or at para. Among ortho and para, ortho is major. Why here, students? Because
Hydrogen
of
bonding.
because of intramolecular hydrogen bonding. Because of intramolecular hydrogen bonding, ortho is going to be major when compared to para. Is that point clear?
Yes, sir.
Yes, right. And now if I want to generate picric acid, if I want to prepare picric acid without any oxidized product, then what you have to do is you can do the sulfonation with the 2 moles of H2S2O7 or 2 moles of H2SO4. You will be generating SO3H at the ortho and para positions. That means after sulfonation, if you try to do the nitration, then this oxidized products will not be obtained. That's the technique. Okay, to generate pure picric acid without any oxidized products, sulfonation is done with the 2 moles. That means what we are doing, the sulfonation means we are actually protecting the groups. We are not making the oxidation happening. Okay, with the 2 moles of H2SO4, if sulfonation has been done, you will be getting SO3H at both the ortho and para positions. So you'll get phenol 2,4 disulfonic acid. After that, if you do treat with concentrated HNO3, you will get more NO2 plus is there, right, in the reaction mixture. So now all the 3 positions are also going to be occupied by NO2. So you'll get picric acid again. To generate pure picric acid without any oxidized product, sulfonation is done with 2 moles, and then benzene or phenol 2,4 sulfonic acid, 2,4 disulfonic acid is treated with a concentrated HNO3. Okay, this is the logic which we are going to follow, so that this SO3H is actually protecting the groups, so it is not making the oxidation of phenol occurring, or you will not be getting any quinones and all. So only picric acid can be obtained. Note, orthonitrophenol and paranitrophenol can be separated using steam distillation. If you remember, we have discussed the purification techniques. Yes or no? In that orthonitrophenol and paranitrophenol, I have given the example for steam distillation. As orthonitrophenol is more volatile than paranitrophenol due to intramolecular hydrogen bonding. Because of intramolecular hydrogen bonding, the boiling point has been decreased or not? Because boiling point will depend upon intermolecular forces. Between one molecule and the other molecule, how much strong attraction is there, that much more thermal energy have to provide, that much higher will be the boiling point. So because of intramolecular hydrogen bonding, what happens? The intermolecular force of attractions in orthonitrophenol will be reduced. Because of that, its boiling point is reduced. Because of its less boiling point, it is more volatile. So we have intramolecular hydrogen bonding here in orthonitrophenol. This is orthonitrophenol. So within the molecule we have hydrogen bonding, but here we have between 2 molecules. Here we have intermolecular hydrogen bonding. Intermolecular hydrogen bonding. So because of this, what you can say, students? Because of this, orthonitrophenol and paranitrophenol can be separated using steam distillation as a technique. Right? So this is the first reaction, like where you have done the nitration of phenol. Phenol is a very good, the OH group in phenol is a very good electron donating group. So it will be increasing the electron density at ortho and para positions greatly. Halogenation of phenol. On treating phenol with bromine, different reaction products are formed under different experimental conditions. Like if I treat phenol with a bromine in the presence of CCl4 or CS2, what you are going to expect? And phenol with Br2 in the presence of H2O, what you will expect? Phenol, if I treat with the bromine in the presence of CCl4 and bromine in the presence of H2O, what are the different set of products you are going to expect? Give your answer, right or wrong. Okay.
So first one only ortho or
First one only ortho or only para? First one ortho plus para. Para will be major. Okay, because of there is no intramolecular hydrogen bonding. So because of to maintain MIMO repulsions, para is obtained. Whereas if you treat with the second compound like Br2 in the presence of H2O, you are getting 2,4,6 tribromophenol, which is a white precipitate. Why? What was the reason? If I treat with only Br2 in the presence of CS2 or CCl4, non-polar solvent, I am getting monobromination. But if I treat a phenol with bromine in the polar solvent like water, you are getting 2,4,6 tribromophenol. Why? Look at the scenario correctly. If I take phenol, the electron density at ortho and para positions is increased only by the electron donating group, that is OH group. And you take Br2 in the presence of CCl4, Br2 in the presence of CCl4. So whatever the electron density we have increased at ortho and para positions in the phenol, that is actually polarizing the bromine molecule. Understand this point carefully. The Br2 is actually non-polar in nature and CCl4 is a non-polar solvent. Bromine is polar or non-polar? Bromine is non-polar because it is there is a bond between 2 bromine atoms. But we are generating Br plus ion. How? The Br plus is generated directly, we are not using any Lewis acid. there is no requirement of Lewis acid. Okay, no Lewis acid required. Why? Because OH is a strong electron donating group. Since OH is a strong electron donating group, the OH itself can polarize Br2. There is no requirement of Lewis acid. What is the role of Lewis acid, students? Like Br2 plus CCl4 we are taking. Earlier we used to take halogenation, means Br2 in the presence of FeBr3, or Cl2 in the presence of Cl2 in the presence of AlCl3. We always take a Lewis acid or not? What is the requirement of Lewis acid? The Lewis acid will actually generate the electrophile. But here phenol itself is a strong electron donating group. Phenol itself has a very strong electron donating group. There is no requirement of Lewis acid. So directly the pi electron density of phenol, since the electron density is great, so that will directly polarize the Br2 molecule, developing the para-bromophenol. Is that point clear? First point. First point is we don't require Lewis acid. Directly the electron density of phenol is great, so that itself will polarize the Br2, generating respective para-bromophenol and ortho-bromophenol. Out of these two, para-bromophenol will be major because of less repulsions. Everything is fine with respect to Br2 in the presence of CCl4, no Lewis acid and done. But what happens if you take water? Br2 in the presence of water. If you look at the same scenario, phenol plus Br2 plus water, Br2 is it polar or non-polar?
Non-polar.
Bromine is non-polar, which is actually polarizing Br2. Which is polarizing Br2 in the previous case?
Pi electron density.
Pi electron density of benzene. But now, what are the species which can polarize Br2?
Lone pair of oxygen and of water.
Okay, it is not only the pi electron density of phenol can also polarize Br2. Water can also polarize Br2. Br2 plus can react with water to form HOBr and HBr. Yes or no? So in the presence of polar solvent, polar protic solvent like water, Br2 is polarized greatly, and thus we get 2,4,6 tribromophenols, because Br2 polarized greatly means you will be having great concentration for the electrophile. If electrophilic concentration is great, obviously you are going to have all the available positions, that is ortho and para positions, which are electron rich, they will be occupied. So you will be getting 2,4,6 tribromophenols, which is a white PPT is going to be obtained as a major product. Is that clear, students? Everyone? 3
Yes.
points you need
Yes.
to understand in 3 points you need to understand carefully. First point, you don't require Lewis acid. Why? Because OH is a very good electron donating group. Second point, see, although OH is a very good electron donating group, if you treat phenol with Br2 in the non-polar solvent like CCl4, you get only monohalogenation happening. But if you treat the phenol, the third point is, if you treat phenol with bromine in the presence of a polar protic solvent like water, you will be getting 2,4,6 tribromophenol, which is going to be white PPT. The difference between these two is, in the presence of polar protic solvent like water, the polarization of Br2 to generate an electrophile is high. Why? Because H2 is also polarizing Br2 and also phenol. Now everything is same. I am replacing phenol with aniline. What is going to happen? Everything is same. Okay. If I replace phenol with aniline, the OH is a very good electron donating group, or aniline is a very good electron donating group?
Aniline.
Aniline.
Aniline, obviously, because nitrogen is less electronegative. Nitrogen is going to be less electronegative when compared to oxygen. So lone pair of electron present on nitrogen will be a better electron donating into ring. So in that case, Lewis acid is required or not required? First, Lewis acid is not required because NH2 is a very strong electron donating group. And if you treat aniline with Br2 in the presence of CCl4 or Br2 in the presence of water, in both the cases, you will be generating 2,4,6 yes or no? You will be generating 2,4,6 tribromo aniline. That means from this, what you can understand, NH2 is a very strong electron donating group. So with the phenol, you are getting Br2 in the presence of CCl4, monobromo product, Br2 in the presence of H2O, tribromination. But if I take aniline, Lewis acid not required, whether it is Br2 in the presence of CCl4 or Br2 in the presence of H2O, it doesn't matter. You will get a 2,4,6 tribromo aniline, because aniline is even a stronger electron donating group, right? So after that, we can look at the next reaction, like Reimer-Tiemann reaction. On treating phenol with chloroform in the presence of a base, example NaOH, a CHO group is introduced at ortho position in benzene ring. So phenol, if you treat with CHCl3 in the presence of NaOH, this is the first set of conditions. The second set is acidification. You get a 2-hydroxybenzaldehyde or salicylaldehyde. The mechanistic approach we are going to discuss. CHCl3 and NaOH. CHCl3 and NaOH. OH minus is obtained from NaOH. CHCl3. So can I say the carbon chlorine bond is polar bond because the electron density present in the carbon chlorine bond is moving towards chlorine. Because of that movement, this carbon develops great partial positive charge. Because of that partial positive charge, what is going to happen? The CH electron density will be moving greatly towards carbon. And can I say OH minus can pick up this proton? The CH bond will be, this hydrogen connected to carbon in CHCl3 will be acidic proton. Why? Because the CCl3 minus, whenever this CH electron density is given to carbon, you can generate CCl3 minus, which is resonance stabilized. And also, as soon as OH minus picks up this proton, the CH electron density given to carbon, since the carbon chlorine bond is also polar, this chloride leaves. You will generate OH minus picking up proton, you will generate H2O. CCl2 is obtained, dichlorocarbene. Along with that, you will generate a Cl minus. This Cl minus will develop electrostatic force of attraction with Na plus. So I can write Na plus Cl minus. If I take NaOH. NaOH plus CHCl3 gives H2O plus CCl2 plus NaCl. CCl2 is a dichlorocarbene, which is a strong electrophile. Strong electrophile. This CCl2, which is going to be a strong electrophile, that will be reacting with phenol. Now the reaction proceeds in this manner. CHCl3 plus NaOH upon heating forms CCl2 plus H2O plus NaCl. The CCl2, because it has only 6 electrons around the carbon, it has a tendency to accept electrons, so it is a strong electrophile. So phenol upon treatment with OH minus, because base is there in the reaction mixture, it will form respective phenoxide ion, O minus. The phenoxide ion, if you try to draw the resonating structure, O minus comes into the pi electron density moves away. You generate double bond O, negative charge at ortho. And this upon treatment with CCl2, what happens? The negatively charged carbon will try to attack the CCl2 carbon. So in that case, you will generate C double bond O. And this carbon will have a negative charge now, because neutral carbon atom gaining the electron density, it becomes negatively charged. And if you look at the negatively charged carbon, and if you look at this particular structure, it is not aromatic in nature, but initially we have aromatic nature. So CH electron density is picked up by carbon, that is C minus will try to pick up this proton. CH electron density will be coming into pi electron density moving away. You generate O minus, CH, CCl, CCl. Now we have OH minus. OH minus, which was present in the reaction mixture, that will now act as a nucleophile. Earlier OH minus, up to now OH minus acts as a base. It picked up the acidic proton. But do we have acidic proton in this species? No. So it will act as a nucleophile. So if you have 2 OH minus, 2 OH minus will try to replace 2 carbon chlorine bonds. 2 OH minus will try to replace 2 carbon chlorine bonds. You will generate a CHOH, CHOH. 2 OH groups on the same carbon, unstable, so immediately undergo loss of water. Loss of water will happen immediately. So they will generate what? C double bond OH. So whenever you treat with the first set of reagents, you will get this species. And this upon acidification, second set, you will generate salicylaldehyde. OH and C double bond OH. This was the mechanistic approach. Everyone got this or not? Okay.
Yes, sir.
Same mechanism.
Yes.
The phenoxide treated with CCl2 to form respective intermediates. CCl2 with the CH bond, C minus picks up the proton, CH electron and C comes into, then OH minus acts as a nucleophile here. OH minus here in this step acts as a nucleophile. It is replacing the leaving group. Here OH minus acts as a base. OH minus here acts as base because it picks up the proton. And ultimately we have CHOH, CHOH, two OH groups in the same carbon unstable. So C double bond OH, acidification, you get salicylaldehyde. So this is nothing but your famous reaction, Reimer-Teimer reaction. So phenol upon treatment with CHCl3, phenol upon treatment with CHCl3 in the presence of phenol upon treatment with the CHCl3 in the presence of a base will form respective salicylaldehyde. Okay, right. Then comes Kolb's reaction, or Kolb-Sweden reaction. So phenol plus CO2 plus NaOH in the presence of at a temperature like 125 degrees Celsius, 5 atmosphere, and then acidification, second set, you get 2-hydroxybenzoic acid, which is nothing but salicylic acid. How is this reaction happening, students? Same. So first you have phenol treated with the NaOH. OH minus will try to pick up this proton to form respective phenoxide. This respective phenoxide, if you try to draw the resonating structure, O minus comes into C double bond C pi electron and C moves away. Negative charge at ortho, you get C double bond O. Yes or no? So this particular intermediate where negative charge is or electron density more constant or ortho, that will try to attack the electrophile C double bond O, that is carbon dioxide. The negative charge on the negatively charged carbon will attack this particular carbon, that is ortho carbon is attacking the carbon of CO2. The pi electron density is moving away. So we are generating what? We are generating carbon will now have a C double bond O, CO minus, and you have C double bond O here. And if you look at this, it is again resonance stabilized. Initial compound is aromatic nature. So to regain back the aromatic nature, so O minus will try to pick up this proton, CH electron and C comes into, C double bond O pi electron and C moves away. You get O minus here, C double bond OH. So this is a species obtained after first set of reagents. Second set is acidification. So if you treat this with the second set, that is H plus, you get respective OH and COOH groups in this fashion. You are getting 2-hydroxybenzoic acid. You may ask a question, sir, why you are always trying to attack the ortho position, but if you try to write the resonating structure, negative charge can be accumulated at para also. Why you are not doing the para attack? Why? Because if I can write the resonating structure of phenoxide ion, I am getting negative charge at ortho. If I try to proceed, I will get the negative charge at para as well. But I am directly attacking the, like ortho attack I am doing. From the ortho position, whatever the negative charge is there, that attack I am doing. Why? Because that final compound, whatever you are going to have, that will exist, that will exhibit intramolecular hydrogen bonding. OH C double bond OH, OH C double bond OH. Because of that only, ortho substituted products are going to be obtained, which are major products. Is that clear or not?
Yes, sir.
Yes, right. So this is nothing but your Kolb's reaction or Kolb-Sweden reaction. Phenol treated with carbon dioxide and NaOH at 125 degrees Celsius, 5 atmosphere, followed by acidification, forms respective salicylic acid. From this salicylic acid, how to prepare respective aspirin? Last class we have seen that. Salicylic acid to aspirin. Anyone?
Sir, acetic anhydride.
Yeah, acetic anhydride or acetyl chloride. Then what happens? The OH group is now going to be substituted with OCOCH3, which is nothing but your aspirin. If I treat salicylic acid with alcohol or phenol, what happens? Esterification.
C double bond OH.
Yeah, C double bond OH will be converted to C double bond OR dash or OPH, right? All these interlinking you have to remember, because salicylic acid I may not be giving. I will be giving phenol to you. Phenol also I may not give. I'll generate phenol. I'll give benzene. Okay. I'll give benzene or I'll give acetylene. I'll generate benzene first. How to generate acetylene? From acetylene, how to generate benzene? Red hot copper at very high temperature. I'll generate A. A treated with a CH3, CH, Cl, CH3 generates B. B treated with O2 followed by H plus in the presence of H2O generates C. C treated with CO2 and OH minus acidification generates D. D treated with R dash OH generates C. What is E? So acetylene, red hot copper tube or red hot iron tube at a very high temperature generates benzene. Benzene treated with a CH3, CHCl, CH3. What is going to happen in the presence of AlCl3? Let us say you will generate isopropyl benzene, CH3, CH3. Then isopropyl benzene upon treatment with O2 in the presence of H mu followed by acidic hydrolysis produces what?
Phenol.
Phenol. Phenol treated with carbon dioxide in the presence of basic medium and acidification produces what? Salicylic acid. Salicylic acid I am treating with R dash OH. Esterification occurs. OH. You will get E as what product? The product E will be OH group will be here only C double bond O R dash. But here you have to do acidic medium. Okay. Esterification happened. Like that, you can generate a sequence of reactions where one product and the other product can be related. Right. Reaction of phenol with zinc dust and oxidation of phenol. The mechanisms for these reactions are not required. Reaction of phenol with zinc dust. Whenever you treat phenol with zinc dust, you will generate respective benzene and ZnO is going to be released. These two actually proceeds through free radical path. These reactions proceeds through radical path. Mechanism not required, friends. And if you take phenol and try to treat that phenol with Na2Cr2O7 in the presence of H2S4, it will form para-benzoquinone. So this is nothing but oxidized product. Okay, the C double bond O groups are going to be present. Two C double bond O groups. With respect to two C double bond O groups, you have carbon-carbon double bond systems. Phenol reaction of phenol with zinc dust, oxidation reaction of phenol. Phenol treated with zinc dust at a high temperature form benzene plus ZnO. So Zn has been undergoing oxidation to form Zn plus 2. Phenol treated with Na2Cr2O7 in the presence of H2S4 forms respective para-benzoquinone. Okay, these are the oxidation reactions of phenol and reduction of phenol or reaction of phenol with zinc dust. We have to remember this reaction, students, since mechanism cannot be explained because it is very lengthy process. Some 10 to 15 steps are there in the second oxidation reaction of phenol. Then comes the neutral FeCl3 test. If you take neutral FeCl3 test, aqueous solution of phenol reacts with the neutral FeCl3 to form a violet colored complex. So this was the reaction. Phenol, if you treat with FeCl3, you will generate the Fe plus 3 ion and C6H5O minus. The Fe plus 3 and C6H5O minus, the C6H5O minus phenoxide will act as a ligand now and it will form a complex. The coordination number 6 complex is going to be formed octahedral complex FeOC6H5 taken 6 whole 3 minus. This type of complex is going to be formed which is actually violet in color. The phenoxide ion Fe plus 3 will be developing like coordinate bonds are going to be formed with OC6H5. OC6H5. Although here I am writing as the bonding between Fe plus 3 and Fe plus 3 and C6H5O minus as purely electrostatic in nature. As per your which theory states the bonding between metal ion and the ligand is purely electrostatic in nature? According to which theory the bonding between metal ion and the ligand is purely electrostatic in nature? Crystal field theory. Okay. So based on CFT I have written here. So the coordination number 6 complex are going to be formed. The complex is actually violet colored in nature. Along with this, you'll get 3 moles of HCl and 3 H plus ions. So this is actually a test. This is actually a test, a neutral FeCl3 test. Aqueous solution of phenol reacts with a neutral FeCl3 to form a violet colored complex. This reaction is used as a test of phenolic group. Okay. Right. And then you have the next concept, ether, students. Ethers are actually two types, symmetrical ethers and unsymmetrical ethers. Symmetrical ethers means what? With respect to oxygen, both sides if you have same alkyl groups, symmetrical. Unsymmetrical means both sides will be having different alkyl groups. So ROR is a symmetrical ether. ROR dash, where R and R dash are not same, that is said to be an unsymmetrical ether. CH3O CH3, CH3 CH2, O CH2 CH3. These are your symmetrical ethers. Whereas CH3O CH2 CH3, C6H5O CH3, these are nothing but your unsymmetrical ethers. The symmetrical ethers or unsymmetrical ethers, they have different techniques of preparation. One technique, can you just list out from the previously discussed concepts only? Any method where you can generate ether? Like dehydration reaction we have discussed. Dehydration reaction, if you do at lower temperature, what is going to happen? That will lead to the formation of ethers. So first reaction is Williamson's continuous etherification process or SN2 mechanism. So what is going to happen here is, if you take an alcohol CH3CH2OH, treat with concentrated H2S4 at a lower temperature 140 degrees Celsius. If I maintain temperature like 170, what is going to happen?
Alkene.
Okay, alkene dehydration will occur. If I maintain temperature 140, then you are going to have a reaction like SN2 mechanism is going to happen, where ether is going to obtain. What is the first step? First step is same. CH3, CH2OH. Treating with the H2S4 means H plus ions are obtained from H2S4. Lone pair of electrons on oxygen, they will be attacking H plus to form a protonated alcohol. You generate CH3, CH2, OH2 plus. Now we have one more molecule of alcohol, CH3, CH2, OH, and we have protonated alcohol. Alcohols can act as both electrophiles as well as nucleophiles. The protonated alcohol behaves as an electrophile. Why? Because CO electron density is moving towards oxygen greatly. Why? Because oxygen possesses positive charge. Because of that, this carbon has a partial positive charge, electron density moving away from carbon. So other molecule of alcohol where we have lone pair of electrons on oxygen, that will act as a nucleophile. So this oxygen is now going to attack this particular carbon, generating CH3, CH2. Oxygen will have only one lone pair now, OH bond, positive charge. Oxygen is connected with CH2, CH3, and loss of water occurred. And now H2SO4 we have in the reaction mixture, which produces the H plus ion. Along with the H plus, it forms HSO4 minus also. That HSO4 minus will now simply pick up this proton. OH electron density is given to oxygen, generating CH3, CH2, oxygen with two lone pairs and CH2, CH3, which is nothing but your ether. So diethyl ether is obtained whenever you treat alcohol with H2S4 at high temperature like 140 only. Very high, 170 if you maintain, you will get alkene. In that case, you will get diethyl ether as a major product. Like in this particular reaction, you are getting diethyl ether as the major product. So this is also dehydration reaction, students. This is also dehydration reaction, but what type of dehydration it is? It is intermolecular dehydration. You have to understand this, not intramolecular. If intramolecular dehydration occurred, then you are getting alkanes. This is nothing but your intermolecular dehydration. The mechanism, you look at this approach. Okay, you neglect whatever given here. This is a mechanistic approach, proper mechanism. Okay, everyone got the mechanism or not? Yes, right. This method is suitable for the preparation of symmetrical ethers having primary alkyl group only. Why only primary alkyl group? Why not secondary alkyl group?
Because attack is SN2.
Yes, attack is SN2. If I take a secondary alkyl group, then the repulsions are going to be high. Then the attack will not be happening greatly. And why only symmetrical ether? because the same molecule of alcohol is protonated, and the same molecule of alcohol, like alcohol acting as a nucleophile, and the electrophile is the same alcohol which is protonated. So you are going to get R and R only, not unsymmetrical scenario you are not getting. Unsymmetrical ethers when you can get, when you can expect, whenever we have taken mixture of alcohols. When you take mixture of alcohols, like two different alcohols you have taken, then obviously mixture of products you can expect. So this method is suitable for the preparation of symmetrical ethers only. Why? Because same alcohol is acting as nucleophile and electrophile. Electrophile is actually the protonated alcohol, not just alcohol, and primary alcoholic group only because of SN2, because of SN2 attack. Like if it is SN2, the repulsions has to be minimum. So if you take mixture of alcohols ROH and R-OH, then you will get a mixture of products. Like with respect to 2 ROH only, the reaction can occur. With respect to 2 R-OH, reaction can occur. With respect to ROH and R-OH, reaction can occur. Okay. In case of, okay, in this case, mixture of products can be possible. Mixture of products. Whenever we get mixture of products, what you have to do? Again, separation of mixture again is tedious, so that's why we don't choose this method. CH3 CH2OH plus H2SO4 concentrated at 140 degrees Celsius you get ether, diethyl ether. 170 degrees Celsius you get ethene. Okay, here dehydration happened. Dehydration. It is nothing but SN2 attack generating the respective ether. This is the first method, students. Treatment of alcohol with a acid at a 140 degrees Celsius forms respective ethers. Second method, famous method of preparation of ethers, Williamson synthesis, we all know. Williamson synthesis means the alkoxide treated with alkyl halide to form respective ethers. What is going to happen? Alkoxide plus alkyl halide will be forming respective ethers. Like sodium alkoxide we have taken and alkyl halide we have taken, you will be generating ether and NaX. And the alkyl halide has to be primary or methyl. Why? What happened if I take secondary or tertiary? Same here, the sodium alkoxide, whatever we are going to have, that is going to act as a nucleophile and it has to attack the electrophilic carbon. The alkyl halide, whatever the carbon halogen bond is there, that is polar bond. The electron density moves towards halogen. The electron density, since it is moving towards halogen, we get a partial positive charge on the carbon. The partial positively charged carbon has to be attacked by nucleophile in the SN2 fashion. So what is going to happen? If you take a alkyl halide which is secondary or tertiary, in that case, what is going to happen? In that case, there is a formation of alkene also. There is a possibility for the formation of alkene also. If you take tertiary alkyl halide, only alkene is formed. If you take secondary, repulsions are going to be slightly high. So look at the example. We have taken CH3 CH2O minus plus CH3 CH2Br. This is alkoxide. This is respective alkyl halide. This alkoxide, how is it? How this alkoxide can be obtained? Alkoxides, how we can prepare, students?
Alcohol in NaOH.
NaOH alcohol or Na alcohol?
N.
Na, right? Faizan, NaOH will not be reacting with alcohols because NaOH is a not a very strong base to react with a very poor acid like alcohol. Okay. So CH3, CH2OH, if you treat with Na, you cannot use NaOH. NaOH can be used whenever you want to prepare phenoxides. You are getting what? Respective CH3, CH2O minus Na plus, and along with that you will be getting half mole of H2 gas. So this alkoxide is now going to be treated with a alkyl halide. Primary alkyl halide we have to take preferentially so that the O minus can attack this carbon easily, generating CH3, CH2O, CH2, CH3, which is nothing but your ether. You will generate CH3, CH2O, CH2, CH3 plus NaBr is going to be obtained. Since Br minus is lost, you are getting Na plus Br minus, electrostatic force of attraction. So NaBr is obtained. Okay. So Williamson synthesis. When you do the Williamson synthesis, alkoxide have to be treated with alkyl halide. you will generate respective ether, and in this scenario, the alkyl halide you have to take the primary or methyl alkyl halide. Sodium phenoxide plus CH3 can I do? Sodium phenoxide if I take sodium phenoxide and treat that with CH3I, the phenoxide ion can act as a nucleophile. It will attack the electrophilic carbon. You will generate anisole or methoxybenzene. CH3 CH2OH treat with Na or NaH. In both the cases, you will be generating what?
Alkoxide.
In both the cases, you will be generating what? Alkoxide, CH3 CH2O minus, CH3 CH2, CH3 CH2O minus is obtained. That CH3 CH2O minus upon treatment with a CH3I. So negatively charged oxygen will try to attack the carbon, generating CH3 CH2 OCH3. CH3 CH2 OCH3 is going to be obtained, which is nothing but your ether. CH3 CH2 OCH3 is going to be obtained, which is nothing but the ether. Is that clear or not?
Yes, sir.
Very simple reactions. Phenol treat with the Na or NaH or NaOH. In all the three cases, you will be getting respect to phenoxide, C6H5, O minus Na plus. This upon treatment with the CH3 CH2I, O minus will try to attack this particular carbon. So you will generate a CH2 CH3 O C6H5. Yes or no? Like ethoxybenzene is going to be obtained, so which is also called as phenitol. Earlier C6H5OCH3 is obtained, which is also called as anisole. C6H5O minus Na plus treated with CH3CH2I will form C6H5OCH2CH3, which is nothing but phenitol and also called as ethoxybenzene. Same reaction SN2 attack is going to happen. A plus B, A is a substrate, B is an alkoxide. We are generating respective ether in this fashion. And which set is preferred? CH3CH3X plus CH3CH2O minus, or CH3CH2X plus CH3CH3O minus. Which set is preferred?
B.
Obviously, the alkyl halide you have to take is a primary or methyl alkyl halide. If you take the first set here, whenever this particular alkoxide is attacking this particular carbon, it experiences more repulsion. So here you have easy SN2. Easily SN2 can occur. So in the set B, you will be generating respective ether. If you take set A, you will be getting ether plus alkene mixture. So the preferred synthesis is the one that involves alkyl halide with a greater SN2 reactivity. So obviously set B is the right option. Very good. Okay. The preferred synthesis is the one that involves alkyl halide with greater SN2. Which alkyl halide will have greater SN2? The primary alkyl halide. So obviously that is going to be the correct set. Compare here A plus B gives rise to CH3O, CCH3, CCH3, CH3. So which set is preferred again? CH3X plus CH3, CCH3, CCH3O minus. And option B you have CH3, CCH3, CCH3, CX plus CH3O minus. Which is the correct set?
A.
Very simple reactions. A set is preferred because alkyl halide has to be methyl or primary. So greater SN2 is going to happen. So option A, that is set A, is going to be the correct set. Substrate plus alkoxide. Here prefer which is the correct set? Substrate plus alkoxide we have been given.
B.
B.
A or B?
B.
B.
Why not A?
Partial double bond character.
Very good. Okay. In aryl halides, CX bond exhibits partial double bond character and thus cannot be broken. Partial double bond character and thus cannot be broken. So obviously this cannot be taken. First set CX bond cannot be broken. So CH3X phenoxide, this is possible. So set B is the correct option. Right? Which of the following ethers cannot be synthesized using Williamson's ether synthesis? So I'll be giving different sets of ethers to you. Yes, these ethers I have given to you. Which of the following ethers cannot be prepared by Williamson synthesis? Like you list out all the ethers which can be prepared, which cannot be prepared, like that. You'll get an idea. Like first ether can be prepared or not?
Yes, sir.
Yes.
You can prepare this because I can take CH3, CH2, O minus. The first one, for the first one I can take CH3, CH2O minus, Na plus, and a CH3I. So first one I can prepare. Second one,
Yes, sir.
second one also I can
Yes.
prepare. So if I want to prepare second one, I'll take CH3, CH, CH3, O minus, Na plus, and CH3, CH2I. So I can prepare second one also. Not an issue. Third one.
No, sir.
No,
Third
No,
one,
sir.
if I want to prepare third one, I have to take CH3, CCH3, CCH3, O minus, Na plus, and CH3, CCH3, CCH3, Br. So this is not possible because it is tertiary alkyl halide. Fourth one,
No.
No,
No,
sir.
fourth one you cannot prepare because you have a bicyclic system. It is Bread-Stool violated. Okay. Fifth one,
No, sir.
fifth one, if you want to prepare, you have to take either aryl halide or you have to take tertiary halide. Okay. Either aryl halide or tertiary halide has to be taken, which is not tertiary halide has to be considered. So no possibility. Sixth one,
No,
No,
sir.
sir.
sixth one also no possibility because of, okay, aryl halides will not undergo. Aryl halides do not undergo SN2. So only first and second can be possible. So third, fourth, fifth, and sixth not possible. So at least one of R or R dash must be primary or methyl and sp3 hybridized. This is a condition. Okay, at least one alkyl group like R or R dash group must be primary and sp3 hybridized carbon should be there. It is not sp2 hybridized, sp3 hybridized carbon should be there, and at least one of R or R dash should be primary. Under that condition only you can follow the respective ether. Next, chemical reactions of ethers. Reaction of ether with a concentrated HX, Zesel's method. So if you look at this reaction, ROH, first reaction, concentrated HX, the lone pair of electrons and oxygen will be attacking the H plus ion to form protonated ether. Like alcohol forms a protonated alcohol, ether will also react with H plus to form protonated ether. Alcohol forming protonated alcohol upon treatment with H plus, because lone pair of electrons and oxygen attack H plus. Ether will form protonated ether. Same reaction, lone pair of electron present on oxygen, they will be attacking H plus. So you get R, O, oxygen will have only one lone pair, OR and OH bond with the positive charge on oxygen. Okay. So what happens is R dash OR plus HX gives R dash X plus ROH. So that is how ether is going to be formed. And what was the mechanistic approach which you can think of is R dash OR upon treatment with H plus. That is the HX is there. Lone pair of electrons and oxygen attack the proton. You will be generating R dash OH OR. So with a positive charge on oxygen, it is similar to your oxonium ion. It is also called as oxonium ion. Now understand this carefully. This oxonium ion can be undergoing the oxygen alkyl group, oxygen carbon bond cleavage in two ways, SN2 manner or SN1 manner. It will undergo SN2 manner when the halide ion
When they
attack
are
the,
primary.
whenever we have the least repulsions, then only we can say SN2 manner. SN1 manner is going to happen whenever you are generating 3 degree or more stable carbocation. Understand this point. If I cleave the carbon oxygen bond and I can generate 3 degree or more stable than 3 degree, then only I can say SN1 mechanism is followed. If I am generating 2 degree carbocation and 1 degree carbocation, then you have to go with the SN2 attack. Understand this point? First, ether you treat ether with HX. The lone pair of electrons and oxygen attack the H plus to form protonated ether or oxonium ion. That oxonium ion is now attacked by X minus in the SN2 manner when you are not producing any tertiary carbocation or more stable than tertiary. Like if you have allyl benzyl, then also SN1 is also SN1 only possible. If a tertiary allyl benzene is taken, SN1 is going to happen. If a primary, secondary or methyl are there, then you have SN2 attack. So whenever SN1 is possible, you are getting a carbocation. So rearrangements are also possible in the case of SN1 reaction. So let us look at the examples, you'll get clarity. So I have this particular reaction, students. What is the first step? Lone pair of electron present on oxygen, they attack the H plus. You will generate what? CH3, CCH3, CCH3. Oxygen with only one lone pair, OH bond and a positive charge. Oxygen also connected with CH2, CH3. Now think of CO bond cleavage. If I cleave this CO bond, I will generate positive charge on this carbon. What is that? Primary carbocation. If I cleave this particular CO bond, I will get positive charge on this carbon. Which is that? What is that? Tertiary carbocation. So I can cleave the CO bond to generate a carbocation. Yes or no? So I am going to cleave the CO bond. Now SN2 attack I am doing. SN1 attack I am doing. CO bond is going to be cleaved in the SN1 manner. You generate a carbocation CCH3, CCH3, CCH3 with a positive charge. As soon as CO bond cleaved, along with that you will generate what? CH3, CH2OH. And now this particular 3 degree carbocation is now going to be attacked by halide ion. X minus attacks. You generate what? Tertiary alkyl halide. CH3, CCH3, CCH3X. X is iodine here, so Ci. SN1 cleave bond and create carbocation. This is going to be SN1. Why? Because if I cleave the carbon oxygen bond, I am generating 3 degree carbocation. So SN1 is a possible attack. I will be generating these two as the set of compounds. In this case, what I am going to generate, students? SN1 or SN2?
SN1.
SN1, because if I will be getting lone pair of electrons and oxygen, positive charge OH bond. If I cleave this bond, I will generate positive charge here, which is benzylic. Whenever I am generating benzylic carbocation, I have to proceed with SN1 only. So I will generate PHCH2I plus CH3CH2OH. Because in the first stage I will generate CH3, CH2 oxygen with one lone pair OH bond, positive charge, CH2PH. It will form CH3CH2OH plus PHCH2 plus I minus attacks, generating PHCH2I. So again SN1 possibility. Look at here. CH3, CH3, OCH2, CH3, consonant HBr. First you will get what? CH3, CH3, oxygen with one lone pair OH bond and a positive charge, CH2, CH3. After that you will get SN1 or SN2. You generate SN1 or SN2. You cleave the both bonds. You cleave the CO bond. If I cleave the CO bond, am I getting 3 degree carbocation?
2
If I
degree.
cleave this bond, I'll get a positive charge here, which is what type of carbon 2 degree. If I cleave this bond, I'll get what type of carbon? Primary.
One.
So in both the case, I'm not getting 3 degree carbon. So what I have to do? I have to follow SN2.
SN2.
SN2 means the bromide ion will now attack the electrophilic carbon where the repulsions are minimum. SN2 means you have to think of minimum repulsion. Where the repulsions are minimum? Like A, B.
B.
B, sir.
B.
So Br minus attacks this particular carbon. CO electron is given to oxygen, generating CH3, CH3OH plus CH3, CH2I, CH3, CH2Br. Okay, SN2 happened. SN2 occurred. CH3, CH3OH plus CH3, CH2Br. Be careful. Whenever if you try to cleave the CO bond and generate a tertiary carbocation or more stable than tertiary like allylic, benzylic, in that case only you will generate SN1 attack. If you are cleaving the CO bond and generating primary or secondary, then in that case what you have to think of? If primary or secondary is taken, we have to go with SN2 attack. SN2 attack means the halide ion will attack the least repulsion. Wherever the repulsions are minimum, that particular electrophilic carbon will be attacked by halide. SN2 attack at the carbon where steric hindrance is less. CH3O, CH2, CH3. First step is what? Generating CH3OH, positive charge on oxygen, CH2, CH3. I can cleave this bond. If I cleave these two bonds, I'll be getting methyl and primary. So it is going to be SN1 or SN2?
SN2.
SN2. So I minus will try to attack which carbon? So this CH3
Methyl.
only. Methyl CH3I plus CH3 CH2OH is obtained. But again, what they attain? Concentrated HI in excess. So whatever the CH3 CH2OH we have, that will be again reacting with HI or not? Since
Yes.
HI is in excess, we get first stage as CH3I plus CH3 CH2OH, but excess is there. So ethyl alcohol will react with HI again. So constant HI means lone pair of electrons on oxygen attack H plus. You get a protonated alcohol. So I minus will now attack, generating CH3 CH2I. I minus will now attack this particular carbon, loss of H2 occurs. So you get what? CH3I plus CH3 CH2I. Methyl iodide plus ethyl iodide, they are obtained as a major product. Whenever you treat with concentrated HI and excess, then what is going to happen, students? Then you have to convert the alcohol to respective alkyl halide again because HI is in excess. Is everything clear so far?
Yes, sir.
Yes.
Yes, right. C6H5O CH2CH3 treated with concentrated HI upon constant HI excess. You will get what? Obviously, lone pair of electrons attacks H plus means you will generate this species. OH with a positive charge on oxygen, CH2, CH3. Is there a possibility of CO bond cleavage? Like a phenyl group and oxygen, whatever it is there, that bond can never be cleaved because it exhibits partial double bond character. So you have to cleave the other bond only. And you will be generating what? If you try to cleave the other bond, you can directly form phenol. But if you cleave it this bond, are you generating 3 degree? No. So again, SN2 attack is going to happen. So I minus whatever it is there, that will attack this particular carbon. CO electron density is given to oxygen. So you generate what? Phenol plus CH3, CH2I. This CH3, CH2I upon treatment with again CH3, CH2I plus phenol is obtained, right? So that is the only possibility, and you cannot convert the phenol to respective aryl halide because OH bond can never be cleaved. Even though you treat a constant HI in excess, this OH bond cannot be replaced due to partial double bond character. Here what happens?
No
C6H5,
reaction.
no reaction because you are not going to have the cleavage of any bond. No reaction because both the CO bonds exhibits partial double bond character. So you cannot cleave the CO bond easily if the oxygen is connected to the phenyl ring. So no reaction is going to happen in the last case. Right, students, let us proceed further. Reaction of ether with H plus in the presence of H2O. Same again. H plus in the presence of H2O. Earlier we have taken HI, right? So here H plus in the presence of H2O. What is going to happen is first lone pair of electrons and oxygen, they will be attacking H plus to form oxonium ion or protonated alcohol, protonated ether. Now what is a nucleophile? Earlier what is a nucleophile in the second step?
Halogen.
Halide ion. Yes or no? Now which is acting as a nucleophile? Water. H2 is there, right? That is the water. So again I can write the same manner. ROR treated with H plus. ROR dash, let us say. ROR dash treated with H plus will generate RO plus OH OR dash with one lone pair. Now it will undergo SN2 and SN1. SN1 means you will generate R plus and then H2O attacks. You generate ROH2 plus. Finally, you generate alcohol ROH. SN2 means H2O directly attacks, generates ROH2 plus R dash OH. This ROH will again form loss of H plus occurs. Loss of H plus occurs. You generate ROH plus R dash OH is there. Here also, as soon as the carbon oxygen bond is cleaved, here you generate R dash OH. SN1 means you have to generate whenever 3 degree or more stable than 3 degree is obtained. When you have to go with the SN1 path, when you are getting 3 degree carbocation or more stable than 3 degree carbocation, then you have to go with the SN1 path. If methyl primary or secondary, in that case you have to proceed with the SN2 path. Is that logic clear or not? SN2 path you have to follow whenever you have methyl primary or secondary. SN1 you have to follow whenever we are producing 3 degree or more stable than 3 degree carbocation. You may ask a question, sir, however, whatever the attack you do, both are alcohols only, R dash OH and ROH you are generating. Then what is the issue? If I do SN1 or SN2, I am getting same alcohols, both alcohols I am getting. But it is okay whenever I give H plus in the presence of H2O, but you will get different products if I give D plus in the presence of H2O. Are you getting that logic or not? If I give D plus in the presence of H2O or H plus in the presence of D2O, then you can have difference. Is that clear, students? Like you give an alcohol like this in this manner, CH3, CH, CH3, O, CH2, CH3 in the presence of D plus and or H plus in the presence of D2O, let us say. H plus in the presence of D2O and same reaction in the presence of D plus in the presence of H2O. What you are going to generate? Here, first case, what happens? You will generate CH3, CH, CH3, OH bond with lone pair of electrons and oxygen and a positive charge and CH2, CH3. Now H2O has to attack. H2O will be attacking, D2O will be attacking in the SN2 manner or SN1 manner?
SN2.
SN2, because if I cleave the CO bond, I am not generating 3 degree or more stable than 3 degree. So I have to go with the SN2 manner. So lone pair of electrons and oxygen will attack A and B. If I take A and B, which carbon get attacked? B.
B.
Right? Because of less degree repulsions, you generate CH3, CH, CH3, OH plus CH3, CH2. Oxygen is connected with the 2 deuterium ions, 2 deuterium atoms. Now only 2 deuteriums and only one lone pair oxygen and a positive charge. Finally, you get loss of D plus to generate CH3, CH2, OD. CH3, CH2, OD and CH3, CH, CH3, OH. These are the two set of products obtained. Do the second reaction like D plus in the presence of H2O. You will generate CH3, CH, CH3. Oxygen is connected with the deuterium now. OD, one lone pair and a positive charge connected with CH2, CH3. Now this is going to be attacked with H2O. Lone pair of electrons present on oxygen, they will attack. Again, if I give A and B, they will attack B carbon only, SN2 attack. you'll generate what? CH3 CH OD CH3 plus CH3 CH2OH. So these are the set of products obtained. They are different or same?
Different.
They are going to be different because whenever I introduce an isotope like deuterium, then you are going to have difference. And not only D plus in the presence of H2O or H plus in the presence of D2O, I can also include H plus in the presence of H2O O18. I can also give O18 also, right? Here oxygen is O16. I can include O18 oxygen. There also I can make the difference, like where I am getting O18, where I am getting O16. That difference can also be included. So you have to be careful while doing it. Right, students, let us proceed. The next and last type of reactions of ethers, like whenever you have electrophilic substitution reaction, ether is the electron donating group or electron withdrawing group?
Electron donating.
Electron donating group, and it is ortho-para-directing or meta-directing. Electron donating groups are ortho-para-directing. And among ortho and para, which is major and which is minor here?
Para.
Para is major because there is no intermolecular hydrogen bonding. So what is the electrophile in first case? CH3Cl, AClCl3, CH3 plus. Second case CH3 C double bond O plus. Third case NO2 plus. So we have the electrophile substituted para positions in all the three cases. These are the respective compounds obtained. Is that clear or not? On the para
Yes.
position, the electrophile is going to be simply substituted because OCH3 is an electron donating group. Because OCH3 is an electron donating group, on the para position, you will be having the substitution of that particular electrophile happening. And the last set of reactions which you can include after this electrophilic substitution is electrophilic substitution, same mechanism, everything is same. Electrophile is going to be attacked by the pi electron density. The reaction is going to happen. You get a Wieland complex, a Wieland intermediate or sigma complex, which is again going to regain the aromatic nature, and because of that it will be proceeding like CH electron density will be coming into the ring. Same reactions whatever we have studied. Right, students? Then let us go with the system of reactions where you can understand about cyclic ethers. Cyclic ethers, you know, any simple cyclic ether which you can think of is, what is the simplest cyclic ether which you can think of? Can I say oxyrene? CH2, CH2, OCH2. Can I say oxyrene, students?
Yes.
Cyclic ether or epoxides. Ring opening in epoxides we'll discuss. Okay, epoxides are a good epoxides. They have a good leaving group? Epoxides. A simple epoxide which you can consider is this one. Epoxides do not have a good leaving group. Epoxides do not have a good leaving group, but still they undergo but still they undergo attack by the nucleophile very fastly to come out of the ring strain. But still they undergo nucleophilic attack to come out of the ring strain or three-membered ring strain, because epoxide is three-membered. So to come out of that three-membered ring strain, so these epoxides will be readily attacked by nucleophiles. Let us take an epoxide. Yes or no? A ring opening of epoxides in a base catalyzed. Two types of ring openings are there. A ring opening of epoxides in a strong nucleophile like Cn minus, R minus, Mgx, that is Grignard reagent, OH minus, SH minus, or ring opening in epoxide in a strong nucleophile or base catalyzed ring opening, That means what happens in this case? If I have an epoxide, I can think the CO bond can be cleaved because carbon-oxygen bond, carbon will get partial positive, oxygen get partial negative. This bond can also be cleaved. If I take a symmetrical epoxide in this scanner, there is no issue. I can attack either A carbon or B carbon. A carbon or B carbon. But now I have to make it unsymmetrical. Yes or no? Let us make the unsymmetry. Let us keep a substitution here. Now I am treating this with a Grignard reagent, let us say CH3MgX, CH3MgBr. Now this carbon oxygen bond is also moving. This carbon oxygen bond is also moving. This CH3 minus MgBr with a positive on magnesium. Grignard reagent can act as a nucleophile, or it can also act as a base. Here it will act as a nucleophile or a base.
Nucleophile.
Nucleophile, because there is no acidic proton in this particular cyclic ether given to you. So it will act as a nucleophile, but there are two positions, like A position and B position. The CH3 minus will attack which position? Either A position or B position?
A position.
A position. Why? Whenever we have a strong nucleophile or base catalyzed opening, the CH3 minus will choose the SN2 path only. The CH3 minus will choose the SN2 path only. It will attack the A position. And the CO electron density is going to be given to CO electron density is going to given to oxygen. So generating what, students? We have CH3 connected to CH, CH connected to O minus. O minus will have electrostatic force of attraction with MgBr plus. CH also connected to CH2. This CH2 is connected with CH3. This upon hydrolysis, this upon H plus in the presence of H2O, it forms what? CH, OH, CH, CH3, CH, OH, CH2, CH3. Everyone got this or not? This type of alcohol is obtained. CH3, CHOH, CH2, CH3. This is going to obtain. Along with that, you get MgBrOH. Whenever the ring opening in epoxide is happening in the base catalyzed or in the presence of a strong nucleophile, you have to choose the SN2 path where you are going to have, SN2 path means it will be completely depending upon steric repulsions. So less sterically hindered carbon is going to be attacked by nucleophile. But the same reaction I can do with an alcohol also. Like the same epoxide, ring opening of unsymmetrical epoxide. Whenever we have symmetrical, there is no issue. I can attack the nucleophile on any carbon. Both are same. Ring opening of unsymmetrical epoxides in acid catalyzed medium. Like I have taken unsymmetrical, same epoxide I have taken. I am treating this with a H plus in the presence of CH3OH. H plus in the presence of CH3OH. What happens now? First step, same. Lone pair of electrons and oxygen, they are going to attack the H plus. As soon as the lone pair of electrons and oxygen attack the H plus, you get OH bond. One lone pair acids and a positive charge. And now what is going to happen is, oxygen possesses a positive charge. Now the CO electron density is moving to oxygen. CO electron density is moving towards oxygen greatly when compared to earlier scenario. Now, whatever the partial positive charge developed here, that is more, and these carbon atoms are resembling the carbocation systems. They are not carbocations, but they resemble the carbocation. Now, whatever the nucleophile will have, that will attack the electrophilic center. But which center? A or B?
B.
B, because the CH3OH is now going to act as a nucleophile. It is going to attack the B carbon because on the B carbon more positive charge developed, because it is resembling a 2-degree carbocation, whereas A resembles only a primary carbocation. So CH3OH will now attack in the SN1 manner. In the acid catalyzed reaction, SN1 manner is going to happen. Why? Why here SN1? Why not in the previous case? Because in the previous case, the CO electron density is moving towards oxygen just to come out of the ring strain. But here CO electron density is moving towards oxygen, not only to come out of the ring strain, but also oxygen possesses a positive charge. So movement is great. So this carbon is going to be electrophilic more. So it resembles like a carbocationic system. So what is going to happen now? So the B carbon, so we have CH3. CH3 is connected to this particular CH. CH is again connected with the oxygen. OCH3. Oxygen has two lone pairs, now only one lone pair and a positive charge OH bond. The CH is again connected with CH2. CH2 connected with the OH. Because CO electron density is given to oxygen, so it is connected with OH. Ultimately, again, loss of H plus will occur, forming CH3, CH, OCH3, CH2OH. This is going to be the respective major. Okay. In base catalyzed or strong nucleophile, that means the lone pair of electrons and oxygen, if they attack H plus in the first step, it will follow SN1. If the lone pair of electrons and oxygen is not attacking H plus, because there is no H plus first of all, in that case SN2. Got it? In acidic catalyst, you can say SN1. So this is about the ring opening in epoxides. Okay, students, these are the different reactions which you can study in ethers and along with their mechanistic approaches, and which are possible, which are not possible. So in the next class, we have our session as it is. We have our session at 3:30, right? So that class you attend as it is. It will be generally, I'll be continuing with the session. We are going to start with the next functional group like carbonyl compounds, aldehydes, ketones, and different reactions involving all those compounds. Fine. Thank you all, everyone. Bye.
Thank you.
Thank you, sir.
Thank you, sir.